Good day. Welcome to the Cool Fish channel. Today I'm going to talk about the Kramers-Krönig relations. Okay, so these Kramers-Krönig relations um, describe how the imaginary and the real parts of the susceptibility are related, or the response function. Okay, so this is actually, we are within the context of linear response theory. And the idea is the following. So your experiment might be that you have some sample, okay, and you interrogate it with a probe. Okay, so this probe could be various things. I'm going to talk about that shortly. So you send in some kind of probe which will perturb your system, and then you actually do an experiment on the response of the system to this probe. Okay. Um, um, so you could say, well, the two concepts you need is, I'm going to call it f of t, and that's a generalized force. Okay, and a generalized force is something that you apply to your system. So this might be a generalized force. Okay, and then your system starts to respond to it, and then what you actually measure is the generalized displacement. Okay, so these are the two central quantities that we are going to be talking about. And let me give you a few examples. So you could, for example, send in an electric field, a time-dependent electric field, which of course alters the polarization in the system. Okay, and then you would be looking at the polarization as a function of time after this perturbation. But that doesn't need to be so. Another possibility is to interrogate your system with a magnetic field, okay, and then look at the magnetization. But there are many others. So you could vary the pressure in the system, and then the volume of the system would respond, or vary the surface tension, and then the area would respond, or a tension. You could make a time-dependent tension. These all have to be time-dependent. I just dropped the notation, and then the length of the system would vary in time afterwards. Okay, and one thing that's common to these pairs, though, is that f times x has to give you dimensions of energy. Okay, so in a sense, work is done on the system when this happens. Okay. Now, there's actually one other basic thing that I would like to just say, that the essential concept here is going to be causality. Okay, so that's really the theoretical content of this exercise. What is the effect of causality on the response functions? Okay, so how does causality affect the response functions? That's what we are going to talk about. Okay, and to start with, so let us start with how our system is responding. Okay, so I'm going to average this quantity, this generalized displacement, and I can write, in the most general case, the probe started at the generalized force started acting on the system at minus infinity, and at most it could act until time t. Okay, and here we have dt prime. It's an integral, and I'm going to define a response function. Okay, so the force acts at time t prime. Okay, and this response function accumulates all the effects of the force. So this we call the response function. Okay, and now one thing I'm going to do is I'm going to say that my response function is 0, okay, if t is, its argument is smaller than 0. Okay, and this of course is the implementation of causality. So this is the implementation of causality. And what I can write then is that x of t is minus infinity to plus infinity dt prime chi t minus t prime f of t prime. And now we're going to switch to Fourier transforms. But we have to define those first. So we're going to say that the Fourier transform, for example, of this quantity x is, well, I guess we can average it, but is going to be 0 minus infinity to plus infinity dt e to the minus I omega t x of t, sorry. Okay, and similarly, we can Fourier transform all the other quantities. Okay, but I should also define the inverse of the Fourier transform. Okay, so for I'm writing it for one particular function, but it holds for all of them. So this one and this one too. This is 1 over 2 pi minus infinity to plus infinity e to the I omega t. Let me put that dt there. Okay, and this is x of omega. That's the inverse of the Fourier transform. And this equation actually, so what you can do is substitute. Okay, so you can substitute the inverse Fourier transform inside here. And what you will find is, well, this is actually a well-known equation in Fourier transform theory. So this is what is known as a convolution. This is a convolution, and the Fourier transform of a convolution becomes something way simpler because it's going to be a product. Okay, so it's going to be just the product. So basically the Fourier transform of the response, okay, so this averaged x of t, the Fourier transform of the response is simply the Fourier transform of the response function, okay, and the Fourier transform of the force. Sorry, I should really say it like this. The Fourier transform of the average displacement is the product of the Fourier transform of the response function times the Fourier transform of the force when we are in frequency space. Okay, so this is true. Okay, now for the response function, okay, so response function chi of t is a real function. Okay, but that does not mean that its Fourier transform is still real. Okay, so its Fourier transform is not a real function in general. And we can write, this is the usual notation that's used in this business. This is the real part. And this here is the imaginary part with the double primes. Okay, and what we want, what the Kramers-Krönig relations establish is a relation between the real part and the imaginary part. Okay, but let us actually just take a look a little bit about what's going on. So if I actually go to this relation, okay, so this relation, the force, so basically what we see is that via the fact that this is real and this is imaginary, that's going to determine whether the displacement is in phase or not with the force. Okay, and chi prime omega, okay, so this component of the displacement, so chi prime omega times f times omega, that's, so here in this case x omega is going to be in phase with the force. But you're going to also have another where this is not in phase with the force. There's actually a difference in phase of pi over 2 via the fact that this has an I in front of it, okay? And this term we call the dissipative term. So this is how the dissipation occurs. Okay, now what we want to do actually is investigate how these two are related, and the way we're going to do it is we're going to first define a function y of t. Okay, and what is this y of t going to be? Well, it's going to be chi of t when t is greater than 0, but minus chi of t absolute value when t is smaller than 0. Okay, so notice that this is actually an odd function in time. And since it's an odd function in time, if I Fourier transform this, I should get something that is purely imaginary. Okay, so ft, Fourier transform of y of t, is purely imaginary. Okay, and let us see that for ourselves. So basically, I want to Fourier transform y of omega. I'm going to, of course, use the formula dt e to the minus I omega t, y of t. Okay, but via this definition up here, via that definition, what we can say is this is actually, I can break it into two pieces, right? So I can say 0 to infinity dt e to the minus I omega t chi of t, okay? And then my second piece, well, here's a minus sign, so I'm going to put that minus sign there. But it's going to be minus infinity to 0 dt e to the minus I omega t chi of minus t. Okay, and then what I'm going to do is in this piece, I'm going to send t to minus t, and I get 0 to infinity dt e to the minus I omega t chi of t. Okay, and when I send t to minus t, I'm going to have, well, I'm going to have, because of this, that this is going to be a plus, this is going to be infinity to 0, dt e to the I omega t chi of t, okay? But I'm going to switch this in order to make it consistent with this one. So I'm going to switch the limits here. Okay, so finally I'm going to get y of omega equals 0 to infinity dt e to the I omega t chi of t minus 0 to infinity e to the, what is dt e to the minus I omega t chi of t. Okay, so that's, well, actually, it's the other way around. This was minus and this was plus, sorry. Okay, so what we're going to have here, though, is, so it's easy to see that this is actually 2I times 0 to infinity dt chi of t. Well, I guess you could say minus sine omega t here. Okay. Yeah. So that's so this y of omega. So y of omega is the imaginary part of the Fourier transform. Actually, I should say y of omega over t is actually the imaginary part of the Fourier transform of the response function. So this is actually I times chi prime prime omega. That's what we have shown here. Okay, and we're going to use that shortly. Okay, but let us go back to y of t. Okay, so we said that y of t, okay, we have a certain definition for y of t. Okay, so it's here. Okay, but we can also say the following, that y of t, theta of t is equal to chi of t. Okay, what do I mean by all this? Well, theta of t is the so-called Heaviside function. Okay, so that theta of t is the Heaviside function, and theta of t is actually 1 if t is greater than 0, and 0 if t is smaller than 0. So that's how it's defined. Okay, and now, and obviously, so this gives me the right response function. Okay, so this is how I define my y of t. So this is consistent, and the point is that we can now look at this equation, okay? And remember that this equation here corresponded to a convolution, okay? And this is what you could say is an inverse convolution, because based on this, you can write that for the Fourier transforms, it should hold that this is 1 over 2 pi integral d omega prime minus infinity to plus infinity theta omega minus omega prime y of omega prime. Okay, so so from this equation we get this we inverted the convolution by writing it in frequency space. Okay, and then the next step is to investigate what this is, because this is actually the Fourier transform of our original Heaviside function. But the problem with this actually, so if I want to Fourier transform a Heaviside function, I want to go to a theta omega, and suppose I have minus infinity to plus infinity e to the minus I omega t dt theta t. Well, that's going to give me 0 to infinity e to the minus I omega t dt theta t. Fine. So the theta t actually becomes 1. Okay. But this does not converge. Okay. However, what we're going to do is instead of 1, okay, so instead of this 1 here, we're going to replace that. Okay, so we're going to replace that by e to the minus epsilon t. Okay, we're going to then do our Fourier transforms and everything. And then we're going to take the limit as epsilon goes to 0. That's what we're going to do. So we're going to define our theta omega by as 0 to infinity e to the minus I omega t e to the minus epsilon t dt. And if we evaluate this integral, it's going to be e to the minus epsilon plus I omega t over minus epsilon plus I omega 0 to infinity, right? So that's so in the end all we're going to get, because at infinity this actually disappears, so all we're going to get is 1 over epsilon plus I omega. Okay, so that's our theta function. However, that's not easy to apply yet, so we have to actually work on this a little bit more. So what we found so far is that our theta function has a Fourier transform, which is 1 over epsilon plus I omega, or we can write this also as epsilon minus I omega over epsilon squared plus omega squared, right? And then if we take the limit as epsilon goes to 0, well, there's one problematic aspect here, okay? So first, let me write this in 2 pieces, epsilon over epsilon squared plus omega squared minus I omega over epsilon squared plus omega squared. Well, in this one, it's easy to take the limit. If I take the limit of epsilon going to 0, I just get minus I over omega, okay? Fine, but what about this one? Here it's a little bit trickier, because the limit depends on what omega is. Okay, so if omega is not equal to 0, then if I take the limit of epsilon going to 0 here, I'm going to get epsilon over epsilon squared, okay, which is actually 0. Okay, so if in this case, so let me say epsilon over epsilon squared plus omega squared. Okay, this goes to 0 if omega is not equal to 0 when we take the limit of epsilon going to 0. However, if omega is 0, okay, then what happens? So if omega is 0, then I'm getting 1 over epsilon. Okay, so this actually diverges in that case. Okay, so if omega is 0, then we get a divergence. Okay, but it's actually a useful divergence, because we can show that this is related to a delta function. You can sort of sense this here, right? Because as a function of omega, Okay, so this should be a function of omega, of course, because we're going to take the limit of epsilon going to 0. It shouldn't be a function of epsilon after that. It's some sort of function of omega. But we see that if omega is finite, then it goes to 0. If omega is not finite, it is 0, then this function actually diverges. So it sort of is acting like a delta function. Okay, so let us look at our function f omega. Okay, epsilon over epsilon squared plus omega squared, limit epsilon going to 0. Okay, but what I'm going to do is, well, is to investigate whether this is a delta function or not by integrating from minus infinity to plus infinity d omega epsilon over epsilon squared plus omega squared. Okay, so this, I'm interested in this integral because I know that minus infinity to plus infinity omega, d omega delta omega, well, that just gives me 1. Okay, so what does this give me if I do this integral? Well, it turns out that the way you want to do this integral is by using the residue theorem. Okay, so I'm going to write this as a circuit integral over some contour which I have not specified yet, epsilon over epsilon squared plus z squared. Okay, I can write this as dz epsilon over z plus I epsilon and z minus I epsilon. Okay, and we're going to take the limit of epsilon going to 0 eventually. But here's one thing to note. First of all, what is the residue theorem? Let us recall here that the residue theorem is the following: f of z prime dz prime divided by z prime minus z. This is actually equal to 2 pi I f of z. That is the residue theorem. Okay, and the point is, well, we have to first choose a contour. Okay, so if I have the complex plane, one contour, and the contour, of course, has to include this integral, minus infinity to plus infinity, over the real axis. Okay, so I'm going to integrate minus infinity to plus infinity over the real axis, and I'm going to close the contour in the upper half plane. And then I'm going to have one, so at z equals I epsilon, I have a residue. Okay, so and then this applying this Cauchy integral formula tells me that this integral is actually, well, the epsilon I have to pull out. I'm going to have a 2 pi I, and that's going to be divided. Well, this is actually this one. These two correspond, and z equals I epsilon is where the residue is. Okay, and this is actually inside the contour that I'm integrating. So I have to put that in place of z. So actually I have 2I epsilon here. The 2 cancels, the I cancels, and the epsilon cancels. Okay, so what I'm showing you, what I showed you actually, is that this limiting process gives me pi times a delta function. Okay, because here I obtain the pi. So my final result is that theta omega is pi times a delta function, okay, minus, well, I over omega. But I have to be careful with how I apply this. Sorry, theta omega is pi delta omega minus I omega. I have to be careful with how I apply this. Okay, so I now go back to my my susceptibility. So here's my susceptibility defined in terms of the convolution, and so my chi of omega is equal to, well, 1 over 2 pi. Okay, and I have, well, I'm going to write it and I'm going to derive it. So d omega prime. Okay, and here I write pi times delta omega minus omega prime minus I over omega minus omega prime, and then my function y omega prime. So I just made a substitution into this earlier expression. So that actually gives me, first of all, it gives me y of omega divided by 2. So it gives me that once when the delta function hits this. And then it gives me something else, which is, it seems to be minus I over 2 pi minus infinity to plus infinity d omega y of omega prime divided by omega minus omega prime. But we have to be careful with this, because in this case there's a singularity which is actually on the real axis. So we have to, that's a conditionally convergent integral, and in order to make it convergent we have to take the principal value. Okay, so we have to take the principal value of that integral for this to make sense. Now, let me immediately use one thing. Let's immediately use the fact that, so we derived this, right? So y of omega over 2 is equal to I chi prime prime omega. Okay, so if I make that substitution here, well, this is I chi prime prime omega. That's what this is. Minus, so this is going to be actually plus 1 over pi times the principal value minus infinity to plus infinity d omega prime chi prime prime omega divided by omega minus omega prime. Okay, and on this side we have the full susceptibility, so we can actually just write that as chi prime omega plus I chi prime prime omega, and we see that on this side we have a I chi prime prime omega. So what we found actually is that chi prime omega is 1 over pi principal value minus infinity to plus infinity d omega prime chi prime prime omega divided by omega minus omega prime. Okay, and that's one of the Kramers-Krönig relations. Okay, now the other Kramers-Krönig relation, I'm going to leave that as an exercise, but I will tell you that what you have to do is exactly the same procedure, except you choose y of t to be even rather than odd. Okay, so for the other, y of t should be chosen to be chi of t if t is greater than 0, and chi of t like this if t is smaller than 0. And you're going to get something in which it's the imaginary part that's going to be on this side and the real part that's going to be this side. And actually it's only going to be different by a sign compared to this expression. So it looks very similar to this. Okay, now one thing I want to mention is, well, one common thing that one derives from this, one obtains from this, is a so-called sum rule. Okay, so a sum rule is what you get at 0 frequency. Okay, so it's the same expression, principal value integral minus infinity to plus infinity d omega prime over omega prime. So this is known as the sum rule for the real part of the susceptibility. And the last little technicality that I want to just quickly discuss is what do we mean by p principal part of the integral. And here's the problem. So suppose that you have you want to integrate, let's say, from minus 2 to plus 2 dx over x. Okay, so suppose that you want to integrate this. This is a first I'm going to exclude the singularity. You have to I can put the singularity back. So this integral, sorry, I want to actually do this. I mean minus infinity to plus infinity. Okay, and you know that this integral, so the indefinite, if you have no boundaries, so this actually is an ln x, right? So it looks like we should be able to do this, but it's not so simple. Okay, so it's not so simple. Let's do the following. I integrate from minus a to b dx over x. Okay, well, there's a singularity, and that singularity obviously is at x equals 0. Okay, so when you actually do a contour integral, for example, what you want is to exclude that singularity. So let's say here's x equals 0. You exclude that singularity and you go around it. Okay, and then you get half a residue. Okay, so because in principle, if you do it like this, you suppose that you close this contour on the upper half plane. If you do it like this, there is no singularity inside your contour, but you could also go around like this. Okay, well, and then you are including the singularity. Okay. Um, but what I want to actually discuss is what do we mean by principal part? Well, principal part actually just refers to this integral without the singularity. Okay, and that's, like we said, it's conditionally convergent. Okay, and the story is basically this. If I want to integrate, do this integral, I can proceed as follows. So suppose that I have, I don't know, minus a to b dx over x. But my ultimate goal is, of course, this. Okay. And I'm just worried about the non-singular part. Okay. So basically, what I want here is to say, I'm going to say minus a to minus epsilon, okay, dx over x, epsilon 1, let's say, plus epsilon 2 to b dx over x. Okay, and the problem is that you know how to integrate this. It's going to be ln epsilon 1 over a plus ln b over epsilon 2. But the problem is that if I, for example, take epsilon 1 to 0 and take epsilon 2 to 0, these terms actually diverge. However, if I take epsilon 1 equal to epsilon 2, and let's call it epsilon, and then take epsilon to 0, then what happens is that I actually just get ln b over a. Okay, and if b are nice numbers, so that's what this integral converges to, provided that I choose epsilon 1 equal to epsilon 2. So this is actually what we mean by the principal value, that when we do this integral, so and let me just this is the formula that we arrived at. So let's say this one and this one, or actually this one. But the point is that when we do this integral, we have to be careful that there's going to be a singularity, omega minus omega prime. And when we're doing that integral, we have to do it like this. Okay, so we have to do it so that the integral is convergent. In other words, the singularity we already took care of, okay, because the singularity gives us this delta function. But the parts that are close, up to the singularity and after the singularity. So here, this integral has to go from minus infinity to epsilon minus some small number. Okay, so this is going to go from minus infinity to the singularity is at omega. Okay, so omega minus epsilon. And then the integral will continue from omega plus epsilon. So these epsilons have to be the same and go off to infinity. Okay, so that is actually what we mean by this principal part of the integral. Okay, so thank you very much for your attention. That was it for today. This was a discussion of the Kramers-Krönig relations. And so to summarize, what we find is that due to causality, the real part of the frequency-dependent susceptibility is related to the imaginary part of the frequency-dependent susceptibility, and vice versa. It is also true, but we left that as an exercise. Okay, thank you very much, and have a nice day.